So the second talk this afternoon is by Professor Jun Muk Hwang from the Center for Complex Geometry, and his title is Convergence of Formal Equivalence of Submanifolds.
Okay, all right. I'd like to thank the organizers for the opportunity. So this problem I'll talk about is the convergence of formal equivalence. This was studied very much in the 60s and 70s, almost 50 years ago. So let me recall why people got interested in this problem. So there's what's called this tubular neighborhood theorem in differential topology. It's in the smooth category. It states like this. Suppose you are given compact differentiable submanifolds in differentiable manifolds. So C and X and C tilde in X tilde. If there exists smooth vector bundle isomorphism between the normal bundles, then there exists a smooth diffeomorphism of suitable neighborhoods of the submanifold in the differentiable manifold. So here's the picture. So if you have a compact submanifold C in X and C tilde in X tilde, and if there's a isomorphism between the normal bundles, then you can find neighborhood, Euclidean neighborhood, O and O tilde, which are diffeomorphic. So that is this is a basic result in differential topology. So that's tubular neighborhood theorem. And in fact, you can choose the diffeomorphism P such that the given isomorphism between normal bundle comes from the derivative of the diffeomorphism. So that is the statement of tubular neighborhood theorem, and this is not too difficult to prove. So it's one of the basic results. Maybe you can find in textbooks in differential topology. And then people asked whether this holds in holomorphic category. So is there a holomorphic tubular neighborhood theorem? So that is the question. So now let's consider the same situation, but C in X and C tilde in X tilde are now complex submanifolds in complex manifold. And let's assume that there's a holomorphic vector bundle isomorphism of holomorphic normal bundles. Then, well, one would like to say that there exists a biholomorphic diffeomorphism of suitable neighborhoods of the submanifold. So is this true? So that was the question. And this is not true. Okay. And in fact, something much easier cannot be true. So in fact, usually, even if you have an isomorphism of normal bundle, it doesn't imply that the restriction of the tangent bundle of X to the submanifolds are isomorphic. Because in holomorphic category, the normal bundle sequence does not necessarily split. So even this you cannot guarantee. So it's completely false. And then what happens if you replace the condition by this isomorphism between restriction of a tangent bundle to submanifold? Well, even if you assume this is still false. So in fact, you need to assume much more. So people realize that we need a much stronger condition, and that is given by finite or formal neighborhoods. So let's recall the definition. So let I be the ideal shape of compact complex submanifold. And then we consider the L's infinitesimal neighborhood for an integer L, which is just the space, the same submanifold C, but with the structure shift, the nilpotent structure, non-reduced structure, OX modulo I to the L plus 1 power. This is the L's infinitesimal neighborhood. And as an example, the first infinitesimal neighborhood is basically the information of restriction of the tangent bundle to the submanifold. That is the first infinitesimal neighborhood. And then you have the notion of formal neighborhood of the submanifold in X, which is basically you collect all finite infinitesimal neighborhoods all together, and that is a formal neighborhood. And then when you are given two submanifolds, C in X and C tilde in X tilde, we say that there's a formal isomorphism between the formal neighborhood. If there is a isomorphism of each else order neighborhood for all integer L, and such that these isomorphisms are compatible with each other, then we say that this is a formal isomorphism. And the statement of the tubular neighborhood theorem, that there's some submanifold, some neighborhood with the biholomorphic map, actually requires formal isomorphism, because if you have such a biholomorphic diffeomorphism, then it induces formal isomorphism. So this is, in fact, a necessary condition. So the correct formulation of holomorphic tubular neighborhood theorem is something like the following. The problem is that you have a compact complex submanifold, C in X and C tilde in X tilde. Now let's assume if there exists a formal isomorphism of formal neighborhoods, then one asks whether there exists a biholomorphic diffeomorphism of a suitable neighborhood, suitable Euclidean neighborhood. So that is the correct question of holomorphic tubular neighborhood theory. And also you ask whether you can choose this biholomorphic map phi such that the given formal isomorphism comes from derivative of the restriction of the biholomorphic map to the formal neighborhood. So this is the correct formulation of holomorphic tubular neighborhood theorem. And the answer is no. So both answer to both questions are no. So people realize that it's necessary to formulate a condition. So that's what Grauert did in the 60s. So this he named it formal principle. So here's the definition. A compact complex submanifold satisfies the formal principle if the answer to the above problem 1 is yes. So namely, we satisfy formal principle if for any other submanifold in any other complex manifold with a formal isomorphism between the formal neighborhood, that implies that there exists a biholomorphic diffeomorphism of suitable neighborhoods. So if this property holds, then we say that the submanifold satisfies formal principle. And then there's a stronger concept, formal principle with convergence. Sometimes people call it strong formal principle. This is exactly the case where the submanifolds, the answer to the second question is yes. So the submanifold satisfies the formal principle with convergence if the following is true. If given any other submanifold with formal isomorphism, there exists a biholomorphic diffeomorphism of suitable neighborhoods such that this biholomorphic diffeomorphism induces the originally given formal isomorphism. So this is stronger than formal principle. Formal principle does not require the last line. That formal principle doesn't care whether the biholomorphic diffeomorphism induces the formal isomorphism or not. But if you require that the given formal isomorphism come from this biholomorphic diffeomorphism, then we call it formal principle with convergence. So roughly speaking, formal principle means that a formal neighborhood determines the biholomorphic germ of the neighborhood. And on the other hand, the formal principle with convergence roughly says that any formal isomorphism of a formal neighborhood converges. So this is a stronger notion. So formal principle with convergence implies the formal principle, but the converse is not true. So let's give a simple example of this, that the formal principle does not necessarily imply formal principle with convergence. It's very easy. So just any point on the complex line with the coordinates z and any point on the complex line or with the coordinate g tilde, then any formal power series with the first coefficients non-zero defines a formal isomorphism between this formal neighborhood of point 0, O, and formal neighborhood of point O tilde. But of course, this is a formal power series. In general, it does not converge. So you can see that a point in C satisfies the formal principle trivially, but it violates the formal principle with convergence. So this shows that formal principle with convergence is strictly stronger property than formal principle. Now, it is difficult to find examples of submanifold that violates the formal principle. And in fact, essentially, there's only one example we know. This is an example constructed by Arnold in 1976, which is an elliptic curve in a complex surface with a normal bundle of degree 0. And there are other examples discovered, but it's essentially of the same nature. So in that sense, there's only one example we know so far. So formal principles, we know that it's not always true, but discovering counterexample is very difficult. On the other hand, it is difficult to give examples of submanifolds that satisfy the formal principle with convergence. Because a point in a manifold violates the formal principle with convergence. So then what kind of example satisfies this? Is there such example really? So what are examples satisfying the formal principle with convergence? It's not easy. But I will show you some examples. So our main results are some examples of this submanifolds satisfying formal principle with convergence. But to simplify the discussion, from now on, we'll consider only the simplest case of submanifold, P1. So smooth rational curves. Because essential difficulties appear already in this case. That's P1 in complex manifold. That's the question of formal principle and the formal principle with convergence is already difficult in this case. And let's recall some definition. So when you have a smooth rational curve, C in X, the normal bundle can be written as direct sum of line bundles. And we say that the normal bundle is positive if the line bundles are all positive. If the integers k1 to kn minus 1 are all positive, then we say that normal bundle is positive. And the normal bundle is semi-positive if all these integers are semi-positive. And this is equivalent to saying that deformations of the rational curve in X cover a neighborhood of the rational curve. And finally, we say that the rational curve is unbendable if all these integers are either 0 or 1. The name unbendable comes from the fact that in this case, there's no deformation fixing 2 points of the rational curve, so you cannot bend it. So this is what motivated by Morris bend and break techniques, that minimal rational curves have this property that you cannot bend it, so it's unbendable. So that's the definition we use. Now for rational curves, we can state some previous result in the following way. The first, this is the main result people obtained in the 70s. So this is the papers appeared at the same time, almost in the same year, Commichau Grauert and Hirschowitz. They proved that if the normal bundle of the rational curve is positive, then it satisfies the formal principle with convergence. So in particular, for example, that a line in Pn satisfies the formal principle with convergence. So I think this is the simplest example you can give for submanifold that satisfy formal principle with convergence. The proof is not very simple. So even in this case, you need some consideration to prove this. And then a few years ago, I proved this result, that if the normal bundle is semi-positive, then a general deformation of the rational curve satisfies the formal principle. So this general sort of is so replace the positive normal bundle condition to semi-positive normal bundle condition. And instead, we have only formal principle. And in fact, this is originally raised as a question by Hirschowitz. So this answers Hirschowitz's question. But here I need to assume that instead of the originally given curve C, we need to consider general deformation of the curve. So general deformation of the curve satisfies the formal principle. So for example, a line in the Grassmannian satisfies the formal principle. Now the question was that whether in the second case, when you have only semi-positive normal bundle, whether we can strengthen this statement to formal principle with convergence. So that is the question. The motivation for me was that I was interested in minimal rational curves. And minimal rational curves usually have semi-positive normal bundle, but not positive normal bundle. So I like to have such statement for minimal rational curves. So that is the motivation of this study. So when can we strengthen this to formal principle with the convergence? And there's an obvious counterexample. So there's an obvious bad situation. which is, I will name it fibered neighborhood in this talk. We say that a neighborhood of the rational curve is a fibered neighborhood if there is a holomorphic submersion of the neighborhood, a non-trivial submersion, such that the curve is contained in a fiber. So here's the picture. This is okay. Here's the fiber neighborhood. The neighborhood has this fibration structure, and the curve is contained in the fiber. This doesn't. Okay. Sorry. So that is a fiber neighborhood. An example is that if you just take product of the curve with C, then certainly the whole manifold X is a fibered neighborhood. And in this case, you can see that because in the base, formal principle with convergence does not hold. In this case, the formal principle with convergence does not hold. Although the normal bundle is semi-positive, and any deformation of C, so in this case, all deformation of C violates the formal principle with convergence because a point in C violates the formal principle with convergence. So you can see that roughly, you can say that the fibered neighborhood is kind of an obstruction to the formal principle with convergence. So that's the motivation for our main theorem. The first theorem, it says the following. Given a complex manifold, we consider the space of smooth rational curves with semi-positive normal bundle. And we choose an irreducible component, K. And if a general member of this irreducible component is unbendable, and the general member has no fibered neighborhood, then a general member of K satisfies the formal principle with convergence. So this gives us an example where you can strengthen my previous result to formal principle with convergence. And there are many examples where you can apply this, especially minimal rational curves on Fano manifold of Picard number 1. So there are many such examples. For example, a line in Grassmannian satisfied this condition. So previously, my previous result says that a line in Grassmannian satisfies the formal principle. Now you can say that a line in Grassmannian satisfies the formal principle with convergence. This is stronger. And also general line on a hypersurface of degree n minus less than or equal to n minus 1 satisfies the formal principle with convergence.
How do you check the second condition if there's no such label?
That's somewhat involved. One way to do it is you look at the tangent, in this case, for your hypersurface, you collect the tangent to the lines. They span the whole tangent space. So it cannot be contained in some fiber. And as a remark, a general line on a hypersurface of degree exactly n is of course unbendable, but it has a fibered neighborhood because it has trivial normal bundle. So there's a vibration. And in this case, it satisfies the formal principle, but it violates the formal principle of the convergence. So there are many examples you can apply this theory. Now, how do you prove something like this? How do you prove some formal isomorphism converges? there's this lemma which I use. This is a lemma from Kobayashi Nomi's Foundation of Differential Geometry. And you can state it as follows, although they didn't state it this way. Suppose you are given a point in a complex manifold Y, and a point Y tilde, and another complex manifold Y tilde. And consider a formal isomorphism. Of course, there are many formal isomorphisms. So consider some formal isomorphism between them. Now, suppose there exists a holomorphic affine connection, nabla on Y and nabla tilde on Y tilde, such that this formal equivalence sends the affine connection nabla to affine connection nabla tilde. If this holds, then this formal isomorphism converges. That's a simple lemma. It's basically because when you have a affine connection, at each point you have a natural coordinate, geodesic normal coordinates. In this case, it's holomorphic coordinates when the connections are holomorphic affine connections. And this, the fact that the formal equivalence preserves the connections basically say that when it sends the geodesic normal coordinates to other geodesic normal coordinates, and which exactly says it's just a holomorphic map. So this must converge. So this is a very simple but is a useful fact to us, that if you can find some affine connection preserved by the formal equivalence, then you obtain convergence. But in our setting, in the setting of theorem 1, where are affine connections? You have rational curves with some properties. Where are affine connections? So this is the question. And this is what you'll answer. And this, for this, you have to look at a universal family of rational curves with semi-positive normal bundle. So let X be a complex manifold, and let K be an irreducible component of the duality space, which is the same thing as Hilbert scheme in complex geometry. So duality space of smooth rational curves with a semi-positive normal bundle. Then the semi-positive normal bundle implies that the duality space K is smooth. So it is a complex manifold. And also you have the universal family of the duality space. Universal family means that, so this two fibrations, alpha and beta, such that alpha is a P1 bundle, and beta is the evaluation map. Namely, each member of the family C, the corresponding point in the duality space K satisfies that the curve C itself is given by the fiber of the alpha projected to X by beta. So this is the universal family. And in our setting, everything is smooth. So this is just two fibrations or two holomorphic maps over complex manifolds. And here's our second theorem. So let X be a complex manifold and K an irreducible component of the duality space of smooth rational curves is semi-positive normal bundle. Now let's assume that a general member is unbendable and the general member has no fibered neighborhood. Then you have this universal family. And what we can prove is the following. Then there exists a canonical non-empty Zariski open subset in the universal family, and a canonical smooth fiber bundle over the Zariski open subset. and a canonical affine connection on this fiber bundle P. So here you come up with some affine connection. And so this is the affine connection we can use to prove the convergence. Now the statement looks somewhat strange maybe to you. Why suddenly affine connection over there? And so to illustrate, so here's the picture. So theorem 2 says that when you have this universal family of rational curves, there's some Zariski open set W and some fiber space over this Zariski open set W, P, and on this P you have some natural affine connection, nabla. So that's the statement of this theorem. To illustrate this theorem, let's look at a simplistic example. So let X be the Grassmannian. And let's choose K, the space of lines on the Grassmannian. In this case, we have parabolic subgroups, P1 and P2, or the automorphism group of Grassmannian, such that the universal family is just the universal family map is just this quotient by the two parabolic groups. So it's just a relation between this homogeneous space. Because in this case, all spaces are the universal family and all the component of duality space, and all these are homogeneous. So you can write it as this diagram between parabolic quotient by parabolic groups. So that is the case. In this case, our theorem 2, when you apply this, the Zariski open set in the universal family is the whole universal family. And the smooth fiber bundle is just this quotient by group G to the universal family. And the affine connection on this fiber space P is the Maurer-Cartan form on the Lie group G. So in this case, you see that this open set, this quotient space, this fiber space, and the affine connections are all canonically defined in this sense from the geometry of Grassmannian. So that is the statement of the theorem 2 in this example. And here's the picture that when you consider universal family of lines on Grassmannian, the universal family is just these homogeneous spaces. And then the theorem says that there's a Zariski open set. In this case, in the case of Grassmannian, the Zariski open set is the whole universal family. And this fiber space P is group G itself. And the canonical affine connection on the fiber space, in this case, is the Maurer-Cartan form on the group G. So that is the example of theorem 2. And in fact, theorem 2 is a generalization of this example. So we don't need all these groups and homogeneous spaces. So in general, when we satisfy those conditions of theorem 2, there's some fiber space on some open set in the universal family, which has some canonical affine connection. Now, this theorem 2 implies theorem 1. Why? So suppose you have a general member C, and then you have the corresponding fiber of the universal family such that it intersects the open set W. Now, if you have a formal isomorphism from this C to another rational curve in another manifold, then it can be lifted to a formal isomorphism between a point on the universal family because of the functoriality of Hilbert scheme. So any formal isomorphism lifts to formal isomorphism of corresponding neighborhood in the universal family because the construction of Hilbert scheme is functorial. And then this formal isomorphism at the level of a universal family can be lifted to this canonical fiber space P because of the canonicality of the construction. And also it satisfies, it preserves the canonical affine connection because it's also canonical. So sort of you follow this functoriality and canonicality that everything can be lifted to some formal isomorphism which preserve the affine connections. So by the Kobayashi-Nomizu lemma, this converges. And then it converges, what's upstairs is converges, so what downstairs automatically converges. So this way you can prove that this formal isomorphism phi converges at general point of the curve. Then it converges at all points basically by maximum principle. So here's the picture. So suppose you have a formal isomorphism between C and C tilde. Then you have the universal family, and this formal isomorphism can be lifted to the universal family by the functoriality of Hilbert scheme. And then you have this Euclidean, the Zariski open sets, and this canonical fiber space with canonical affine connections. And this map between the universal, between the curves in the universal family can be lifted to the this fiber space because of the canonicality. Everything is canonical, so it can be lifted. And since the affine connections are also canonical, it preserves the affine connection. So it has to converge by Kobayashi-Nomizu lemma. And then so this phi sharp converges, and then it implies that phi flat also converges. So phi itself converges at the point, at general points, but then by maximum principle, it converges everywhere. So this way, you can see that theorem 2, the existence of canonical affine connection in some canonically associated fiber space, that implies the convergence. So this theorem 2 is the main thing behind the convergence. And in some sense, this is more interesting result than the convergence, because it says that general deformation space of certain submanifold automatically has some natural connection. Okay, so how do you prove this theorem 2? So to do that, we need to recall some general concepts. This is some differential geometry concept. Distribution. So let M be a complex manifold. A vector subbundle of tangent bundle is called a distribution, holomorphic distribution. And then we say that the distribution is Levy non-degenerate if the anti-symmetric bilinear map coming from the Lie bracket is non-degenerate for general point. And we say that the distribution is bracket generating if the successive Lie brackets generates the tangent bundle at the general point. So this is a general concept in distribution theory. And then there's the notion of symbol algebra. So given a distribution, for each point, the successive Lie brackets of the distribution determines a nilpotent graded Lie algebra called the symbol algebra of the distribution at that point. And we say that D has isotrivial symbol algebras. If the symbol algebras are isomorphic as graded Lie algebra for all points in a Zariski open subset N. And for example, if you have a contact distribution, then in that case, the symbol algebra is isomorphic to the Heisenberg algebra at every point. So this is the case of isotrivial symbol algebras. Now there's a result in differential geometry. This is Tanaka prolongation theorem, and it's stated as follows. This is proved in 1970. It's very similar to the situation we are looking at. Given a transversal pair of holomorphic submergence, so a complex manifold M with two submergers alpha and beta, such that their fibers intersect transversally. Then you define a distribution by taking the kernel of alpha and beta. So you obtain a distribution on M. Let's assume that this distribution D is Levy non-degenerate and bracket generating and has isotrivial symbol algebras. Then Tanaka proved that there is a canonical non-empty Zariski open subset on the manifold N with a canonical fiber bundle P and a canonical affine connection on this fiber space P. So this statement looks very similar to our theorem 2, but of course the conditions are somewhat not exactly the same as our situation. But this is a general result in differential geometry. So whenever we have two fibrations, transversal fibration, there is a way to construct some affine connection. As long as this distribution has these three properties. So that is Tanaka prolongation theory. Now, if you have not seen this before, then the first question you would ask is, why the hell somebody prove something like that? And what is the motivation with result like this? And there's a motivation. So this theorem is actually generalization of Tanaka's older result of construction of canonical Cartan connection for Levy non-degenerate CR structures. So these are all kind of generalization of Levi-Civita connection Riemannian geometry. So Levi-Civita connection is a canonical connection of Riemannian structure. And Tanaka constructed such a canonical connection for CR structures, non-degenerate CR structures. But in this case, the connection does not exist on the original manifold. It exists on some fiber space. So that's why it's called the Cartan connection. So this is what he proved for CR structure. CR structure is basically in the holomorphic setting. It is a contact structure. So what he proved for contact structure, he generalized to this theorem. So that is the origin of this theorem. It's a generalization of CR geometry to arbitrary double fibration. And here, the canonical fiber bundle P is a tower of principal bundles with different structure groups, of course. And this is, as you can see, that is a generalization of, in the Grassmannian case, generalization of the quotient of group by the parabolic subgroup associated with this double fibration. And the generalization is that Tanaka does not require a homogeneous space. For homogeneous space and homogeneous structure, everything can be explained in terms of Lie theory, but Tanaka sort of generalized it to the situation where the space is not necessarily homogeneous, But instead, he requires some homogeneity. And that is the third condition, that the symbol algebras are isotrivial. So at every point, the symbol algebras are isomorphic. That reflects some kind of homogeneity. So that is Tanaka prolongation theory. Now, let's see whether we can use Tanaka prolongation theory to prove our theorem 2. So this was our theorem 2. We are given complex manifold with a family of rational curves with these conditions on the unbendable, no fibered neighborhood. And then we need something like this, then some fiber space, some open set in the universal family, some fiber space, and some affine connection, all these canonical. This looks very similar to Tanaka's statement, right? Especially the last 3 statements are exactly the same as Tanaka's statement, these 3. So we may try to prove our theorem using Tanaka theorem. It's obvious what to do. So you replace the double fibration by our universal family. And on the universal family, we consider this distribution as Tanaka did by direct sum of the fibers. And then we need to check these 3 conditions. Now it's possible to check that our condition that a general member is unbendable implies that this distribution is non-degenerate, Levy non-degenerate. You can prove this. Also, the condition that there's no fibered neighborhood of general member implies that the distribution is bracket generating. So these 2 conditions are satisfied. Now the problem is the 3rd condition. So isotrivial symbol algebras. Unfortunately, this is not always true. Because in our case, you have essentially just deforming rational curves. There's no reason why there's any kind of homogeneity is not guaranteed. So the symbol algebra in general can change. So we cannot apply Tanaka theorem directly. So what we did is quite general. So we proved generalized Tanaka prolongation theory, which is just removing this assumption 3, the assumption of isotrivial symbol algebra condition. So here's our result, that given any transversal family of holomorphic submersions, and we consider this distribution D, and we require just the first 2 conditions, Levy non-degenerate and bracket generating. And still you can obtain all the results Tanaka proved. So a canonical Zariski open subset and canonical smooth fiber bundle with a canonical affine connection. So in some sense, this is our main result. And the convergence is sort of application of this result. Some remarks. So our generalized Tanaka prolongation theorem proves theorem 2, hence theorem 1. And in our case, this fiber bundle is a tower of not exactly principal bundles, but generalized principal bundles. In the Tanaka situation, because of the isotrivial symbols, you can obtain a tower of principal bundles. But in our case, the structure group cannot be constant. The structure group changes from point to point. So basically, you have some group scheme, and then you consider principal homogeneous space of the group scheme. So that is the main technical difference. And the proof, let me just mention that the main difficulty of the proof is extremely complicated induction argument, because Tanaka's original proof is 70 pages long, and even under the assumption of isotrivial symbol algebras. And probably we couldn't have generalize this, such a complicated proof. But very fortunately for us, Alexevsky and David simplified Tanaka's proof to about 30 pages in 2017. So luckily, we located this simplified proof, and this can be adapted. So our proof is shorter than Tanaka's. And the main technical point is that the connection on principal bundle, which is used in this Tanaka construction and also Alexevsky David, we cannot use it directly here because the structure group is changing. And so we need to replace it by a suitable general concept. Thank you.
Yeah. Okay. So thanks very much for your talk. Are there questions? Yeah.
Thank you, Jun Muk. What is the replacement?
The replacement is a kind of partial connection, and you have to sort of locally you produce local trivialization of group locally, infinitesimally. It's somewhat technical, so you can locally compute. So that the torsion of the connection, some component of the torsion invariant on the invariantly defined. So you can do it only locally, infinitesimally.
Even if the symbol jumps right?
Yes, yes. No, if the symbol jumps, you cannot do it. So this is on the open set where the symbol changes smoothly.
Oh, that's part of it, because
Yes.
it's the definition of.
Yes, yes.
Okay, are there questions?
Initially,
Theorem 2.
Yeah.
Oh, maybe. I'm in this black hole again. Not here.
My question is the some canonical velocity of
Mhm.
the W, the value, but outside that is what is the
The curve outside
the
the
outside what's happening?
what's happening? Okay, so typically outside W, as Colin just pointed out, the symbol algebra can make jump. Then the construction completely fails. So even in Tanaka case, even the symbol algebra, when you construct this, you have to do some algebraic operation. And sometimes along some locus, the algebraic operation jumps. Then you cannot have this construction. So we only look at an open set where everything that is holomorphic smoothly. So that's why we need to exclude some part. Is this the answer?
I have one question about the elliptical case. Some people are really interested in the neighborhood of elliptical.
Yes, many people, yes. I think your student, Koike.
Yeah, I mean.
It's different situation. In the Arnold example, like electric curve on surface, the electric curve is rigid, it cannot be deformed. So our case is different. Our case is a semi-positive normal bundle. In Arnold situation is a flat bundle. The normal bundle is flat. There's no deformation of electric curve. So it's a more topological obstruction. But in our case, this is the case where the curve can be moved. It can be deformed. So it's a different category. Is this your question?
Yeah, but still, maybe you
Our method, I don't think our method works. Our method excludes some special rational curves. And in some sense, Arnold's example belongs to a class of special curve, where it is a counterexample.
said there's a key, this blue bubble key is canonical, and then you construct it as the power of principal bundle.
Yes.
Like, I mean, I can see it's the power of principal bundles. Like, do you have an alternative explanation for that? Because like yeah, it's a power. Maybe it's like a if the principal bundle G is constant, as in Tanaka is the original statement. Maybe it's like a extension of the sequence of extension of G, something like that. But do you have any geometric?
I think it's a sequence of extensions of G, but the G to start with was not a single G, but a family of group scheme. So it's a sequence of extensions of the group scheme. That's it. So that is the best I can.
Thank you.
I'm just wondering, so for your second 1 and 2, so these two conditions, I think the second one is the necessary. And what about the first one?
That's a very good question. Yes, 2 is necessary, but first is not necessary. So I'd like to remove this one also. And the difficulty is in differential geometry. There's you see, when you apply Tanaka, our theorem, generalized Tanaka. Okay, so the difficulty is here that we need a Levin undegenerate condition, and for that you need unbendable condition. Now there are people in differential geometry currently working on removing this assumption, Levin undegenerate, or weakening this assumption to what's called KL non-degeneres. So if they succeed, this is Zelenko, Igor Zelenko and Boris Dubrov. They are trying to generalize this part. If they succeed, then I can remove the unbendable assumption. So the difficulty is in differential geometry. It's a good question.
Okay, so
Okay,
then let's thank Professor Hong again.
thank you.
Okay, so the next talk is 10 past 4. I apologize in advance, it's be a Zoom talk, but it's by it's in person.
Okay.
So it sort of works, right?
Yeah.
Some technical. Okay, thanks very much.